And welcome back. Now today's little project is all about this little device attached to this Arduino. This, in case you don't recognize it, is a piezo sounder. So it's not a loudspeaker, it's actually something that vibrates according to whatever square wave you pump into it. Why am I interested in sound waves and piezo sounders in particular? Well, a few years ago we had a bit of a problem with our fridge and it lost us a lot of money because the door was left inadvertently open overnight. So all the food was spoiled, we daren't eat any of it. So we thought we need a fridge alarm of some kind. And that led me on to a number of discoveries on how to create proper fridge alarms that work absolutely every time. So first of all, let's have a look at the actual fridge in question and what there is at the moment, and indeed why I want to replace what's already there. So this is my fridge. Now let's see what happens when I open the door of my fridge. Did you hear that sound? And listen to what it does when I close the door. That little sound is generated from a little box around the back here, which I'm hoping I can film. There's a little box, power going into it. Now that little box generates the sounds when I open the door and close the door. Not only that, after 30 seconds of keeping the door open, you'll hear a warning beep. So let's speed that up and listen to what the beep sounds like. Did you catch that? Okay, now that warning beep is also generated by the microcontroller at the end. So let's discuss this back at the workbench. So why do I need a fridge alarm? Well, this is what happens. Look, we go to close the door. The door nearly closes, the light goes off, but there's this huge big gap, which means, the door isn't closed at all. In fact, there's some sort of resistance in. The resistance, ironically, is caused by this button here that turns the light off. If they'd only switched the light off by some Hall effect transistor, then maybe this door would close normally. Now we've had this happen in the past, and basically the door stayed open like that all night. All the food has been spoiled, we didn't eat it, not after being brought up to room temperature. But see, now the fridge alarm is going mad because the door's been open a little while. Now, how does it work? Well, basically this device here, which was taken from a burglar alarm casing like you might have on windows and doors, there's a reed switch in here, which may or may not have been part of the burglar alarm reed switch array, but whatever, it's in here anyway, and it's controlled by this magnet here, which just happened to be one I had. See, if I take that away, you see that little dot there, that's where it's got to go. And I keep meaning to paint this white to make it blend into the fridge, but it's been here for about 5 or 6 years and still isn't been painted, so so as this comes close to the reed switch, there we are, you hear the sound. That means it's closed it, and it's only got to move away a very small amount, see, and it's open. So it's that keeps this alarm working well, even though the light is off. So some alarms you put inside the fridge, put them on a shelf somewhere underneath the light, and if the light stays on for too long they'll go off, but of course on this occasion it wouldn't help, because like, the light goes off there. Look at that big gap on that door, wow. So that's why I had to build this on the outside, and that's fine, that's working great, but I do want to enhance this. So let's go back to the desktop or workbench and see what we need to do. Right, so here we are back at the workbench again. Now, what's wrong with my current setup downstairs with the fridge? I mean, it's got a piezo sounder in it like this. In fact, it's got 3 different sounders in it because I was experimenting just a little bit at the time. And what's wrong with it? Well, this is the problem. When you open the door, as you saw in that video clip, it makes a nice little sound as confirmation that the alarm itself is up and running. And when you shut the door, there's a nice little brrr confirmation that the door is in fact closed. Yes, if the door doesn't get closed, you get the warning, but at least you come to recognize that the door has been closed. Now, our cat Benny, whom you may have seen in 1 or 2 of my videos because he's quite interested in electronics generally and more things Arduino, he often gives me advice. He's come to recognise the sound of the fridge door being opened, of course. After all, it does mean food of some kind, or perhaps a little splodge of cream on his food or something. And that's getting a little bit worrying for us, that he keeps running out there, listening for that fridge noise and thinking, food time. Because if there's one thing Benny does not need, it's more food. So I want to be able to disable that noise, but not permanently, just when we choose to. So that's the first thing, and the current setup won't let me do that. It's only on a little tiny 8-pin microcontroller from Microchip, in fact. And there's just not enough inputs on there to do that. So the first thing then I need to do is replace the initial Microchip board I've got in there, and also allow at least one sounder, probably two in fact, a normal sounding one and then a very loud one. And I want to be able to touch something, not this, but something like it, to say, don't tell me the sound when I open the door for this time only. And of course, we've got to make sure that when the door shuts, everything on here stops in its tracks. We don't want any more noises. If it's in the middle of a noise, we want it to stop dead, and so forth. So that immediately probably make you think, yes, an interrupt driven piece of code in some way or form. And just as a bit of historical interest, this in fact was our very first fridge alarm. Now this isn't even a microcontroller, it's an NE555 timer in there, and this is some kind of, I think it's a Velleman kit, doesn't actually say on it as far as I can see. I mean, this is going back to the turn of the century, I think, and basically it was wired up in a similar sort of way, not quite the same. And we had an on time and an off time, and I can't even remember now how it's set up so it didn't drive us mad. Perhaps it did. Maybe that's why it replaced it with a microcontroller one. Well, the time's come now, not just to replace that, but to replace the one that's there and bring it into the 21st century by using Arduino, and it will probably be a Nano when we implement it. One or more tone drivers at some kind of touch sensitive device, and we're not using any external chips. That'll all be done on the Arduino this time. And an interrupt driven piece of code. Now it's simple, straightforward, an easy to do project, and could in fact save you money when the kids leave the door open. Right, let's get something wired up, and I'll show you the first piece of code we need to look at. So I've disconnected from the Arduino board here everything that isn't absolutely essential to making a sound, which leaves us just the piezo. So one side goes to ground, and the other side goes to one digital pin of your choice, really. Now, they are marked on the piezo that one is in fact positive and one is ground, but they're all the same. The center's always the positive. So let's have a look at the code that will make this make a sound. Now, this is simplicity in itself. First of all, we define which pin we're going to run the piezo from. Okay, so on here, this red line goes to pin 8. Then we're going to say how long we're going to actually run the sound for, and then we're just going to pick a pitch at random to start with. So I've chosen 200 Hertz, which is probably about the limit, quite frankly, of one of these. You're not going to get a lot lower than that. So we set the output mode for that pin, because obviously it's an output, so we're going to generate a square wave. And I've just played about here a little bit. I've put this in a loop. So I'm saying play a note for 1,000,000 microseconds. Now you might go, why on earth are we talking about microseconds? Why don't we just do it for milliseconds? Let me explain. What we're going to do is set the digital pin high for the number of microseconds divided by 2 that the frequency is. Why? Let me get a bit of paper and show you. So, piece of paper duly in hand, let's describe what we're going to do. Here's our graph, which is more difficult to draw than you might think, because I'm looking at the camera while I'm doing it. Right, so we're going to generate an output. So time is this way, and plus 5 volts or thereabouts is that way. So we're going to say, right, nothing's happening initially, then we're going to generate a 5 volt pulse, and then that's got to continue for half, 50% of the time of the frequency that we want in order to generate the right tone. So at the moment we're talking about a 200 Hertz cycle, Okay, so that's 200 times a second, and that means we want to have an output for 200, well 100, and then nothing for 100, and then repeat that forever. So half here, half here. There's 50%, there's 50%. Right, that's how you get a balanced square wave. So we're saying, well, if we want 200 per second, that means we want to go high 50% of the time, which is 100, and then low 100 microseconds. Okay, so that's what these, that's the high, that's the low, and they'll both stay high or low for half the pitch value in microseconds. And now we say, well, how long are we going to play this note for? Because obviously if we're talking about 200 microseconds, we're not going to hear anything. We need to extend that to make it at least, you know, quarter of a second or something for us to determine it. So in our duration, we're going to say, whilst it's less than 1,000,000 cycles, which is 1 second, about. Okay. So it's going to generate this square wave, 50% duty cycle, for 1 second, and we should hear a tone from that. Now after 1 second, when we've played this tone, what we're then going to do is reset the duration back to 0 so we can start again, and increase the pitch by another 200. So we started off with 200, and then we're going to go to 400 and do exactly the same, and then 600 and 800 and 1000, okay, for 10 times. So we'll end up with a final pitch of 2000 Hertz, which the ear can hear quite well. So that's all we need. That's all we need to generate a tone. And if you don't want to use a library or something and you've just got something very, very simple to do, this is it. The massive disadvantage with this, of course, is that it's very, very time sensitive. If you're doing other stuff while you're outputting this signal, and of course your output signal won't look like this at all. It'll be all over the place, and it might even be inaudible. But let's upload this and just see what it sounds like. So there it is compiling, and it's uploading. Now I can hear a tone, but it is very, very faint. And why? Well, that's one of the disadvantages of piezo out in free space like this. These two plates are effectively vibrating against each other, but of course there's nothing really to make the sound. What we need is to put this on a flat surface. Normally you'd glue them with the tiniest amount of glue you could ever get away with on a flat surface. Now look what happens if I just put my coaster underneath and rerun that. And I'm just going to hold it down, not with my fat fingers, but with a pencil. So I'm going to restart, just hold it. Now I'm hoping you can hear that a lot clearer now. So that was simply because it had this sounding board to sound against. So when you build this into a case, this piezo, you've got to glue it against the bottom of the case or the side of the case to give it something to vibrate against. And that was actually quite loud. Now if I review this video and found out that it is in fact a bit quiet, I'll amplify it. But in the meantime, let's just play that again. I'll just hold it down. Amazing. Now that's done without any libraries, of course, and each tone was exactly, well I say exactly, more or less 1 second long, because we've said the micros here is going to be about 1,000,000. Well, nobody's going to notice the odd microsecond one way or the other, frankly, when we're talking about fridge alarms. Okay, so that's how we can generate a tone, and that's the basis of how tones are generated using that square wave method I was telling you, and all other libraries will have to use the same method. There's no other way of doing it. Now that's the fundamentals, and you know me, I like to sort of show how it's done before we use libraries, but in the final project we most certainly will, because there are several advantages, not least that we don't have to worry about the timing so much, and rather than doing all this high and low stuff, we'll let the library take care of all that. Okay, so that's the first thing. So we've already got the sound coming out. Now the next thing we really need is some kind of touch sensor that's going to be stable over a long period of time, and given that I need to run a wire from the box where this is all contained in to the front of the fridge, if you remember, there's that burglar alarm sensor at the front of the fridge, so it's got to reach that, and without being interfered with. Let's see if we can find something that's going to be nice and stable. Right, here we are back with the capacitive touch sensor part of this video, and as you can see, it's a very, very complicated circuit because it consists of one resistor and optionally one capacitor. Now, I think anybody will probably be able to cope with that, and it works like a dream, quite frankly. So how does it work? Well, let's give it a whirl in the code window and just see what we've got. Right, so this code window here shows that we've got a library this time called capacitive sensor, and I've looked at the library, and whilst it's not, you know, super complex, it's enough for us to want to use the library and not try to write it ourselves. By all means, go and have a look. It's not the .h one you want to look at, of course, it's the .cpp, but have a look by all means, but we're just going to use it as a black box. So what we're going to say is, first of all, we need to create our object, and I've called it sense because that's what it's doing. It's sensing stuff, isn't it, on this wire here as it happens. Now you have to give it the pins, so 4 and 2, and I'll explain exactly what they're doing. We're doing some initialization here. I'm basically saying go and print me the signal that you're seeing. So rather than going into all the intricacies at the moment, let's upload that and see what happens. Right, so there the debug window is now showing us these values, and these values are basically what the Arduino is picking up from this wire, or what the library is giving back to the Arduino anyway. As you can see, it's in double digits, but not huge amounts. Now if I touch even just the wires, not the bare wire, just like that, look, you'll see it's gone up quite a bit already. Let me zoom in on this a little bit so we can see a bit more. There we are, that's better. Now you're supposed to connect this end of the wire to some kind of piece of foil, a touchpad, anything you like really, not just a bit of wire like I got, but even when I touch the bit of wire you can see how the figures jump up. I mean, that is massive, isn't it? Now if I connect it, say if I use my paper opener, that's metal, that should conduct, so I'll leave that on like that. Right, so it's now in the 200s. So if I touch this, and you see it shoots up to the several thousand. Now you may have noticed that the values now being shown are in the about 200s, the low 200s, because obviously we've adjusted things here, haven't we? We've moved the wire onto a piece of huge big metal that's picking up all sorts of signals. So this is where auto calibration comes in. Now you can force the auto calibration via this bit of code here, which I did have running, which basically says every 5 seconds re-auto calibrate. So take whatever signal you're getting at the moment as the baseline, which it's not doing at the moment. It's taking that signal as a real signal. So in our code, as you can see here, when we set the auto calibration millisecond, that is to say how often do you want to auto calibrate, we have set it to such a huge number it will never do it. But we can do it for every second. It's probably a bit of overkill, but it will prove the point, if nothing else. So where we're going to say, when we run this code, as part of the setup, we're going to say auto-calibrate every 1 second. Now by default, it will do it every 20 seconds, which is much more realistic. But just for demo purposes, I think this is more than enough. So let's upload that. There we go, it's launching. We'll come back to our serial monitor view. Right. Now you can see, even though it's connected to this piece of metal, we're down to almost single digits. And if I touch it, we get that massive spike again. So it'd be very obvious to use this as an on-off switch, wouldn't it? Anything over, wow, even 100 to make it really, really obvious that you're touching something. And I think really that proves that that's all we need to do for our touch sensor. So I can be able to touch a sensor on this project when it's done. It will be detected very, very well. I mean, there's no ifs, buts or maybes. It will be detected, look. And I'll be able to turn off the piezo sounder just for that one door opening session. Well, door opening and closing session. so Benny the cat doesn't come running out thinking he's going to get some food. Simples. Right, let's move on. The next thing we need to do then is put some of this together and get some of the logic working behind the scenes. Who would have thought we could have learned so much just by doing this simple project? So please join me in part 2, which I promise to release very, very soon, because I know how frustrating it can be if you're deep into the heart of a project and then there's part 2 and it won't be released for a week. So I'm going to release that a lot sooner than I would normally. And please follow me on that, because the actual implementation is a joy and you'll see how it works so well. Benny unfortunately won't be quite so happy because he'll be missing out some extra food. Still, join me in part 2 and thanks for watching. I hope you're finding these videos useful and interesting. Please leave comments down below, subscribe, share and give me a thumbs up. Thanks for watching. See you in the next video.